Consider a particle in a one-dimensional infinite potential well with its walls at x is equal to 0 and x is equal to L. The system is perturbed as shown in the figure. The first order correction to the energy eigenvalue is A V0 by 4, B V0 by 3, C V0 by 2, D V0 by 5. So in this question they have asked us to find what is the first order correction to the energy eigenvalue when the one dimensional infinite potential well is perturbed. Okay, so E1 is equal to integral 0 to L psi 1 V of x into psi 1 psi star here into dx. This is a formula to find the first order correction. So the value of psi is equal to root of 2 divided by L sine pi x divided by L. So we need to know what is the value of this potential. So potential can be found by two ways. So first method is, this is the given system. So here it is 0, this is L and this is V0. Now I draw a line somewhere here. Okay, this corresponds to V of x and this is x. So if we take this a similar triangle, the triangles O V0 L and O V of x x are similar triangles. Therefore, their corresponding sides are in proportional. Therefore, V of x divided by V0 is equal to x divided by L. So this implies V of x is equal to V0 divided by L into x. This is one method of finding it, and another method is if we know the value of 2 points in a straight line. So this point is 0, 0 and this point is L, V0. Then we can write y minus y1 divided by y2 minus y1 is equal to x minus x1 divided by x2 minus x1. Here the value of x1 is, this is x1 y1 and this is x2 y2 and the value of y is nothing but v of x. Okay, if you substitute all the values, we will be getting v of x as v0 divided by L into x. In both the ways, we can find the value of v of x. So it is going to be v0 L into x. Now substitute the value of psi and v here. E is equal to integral 0 to L root of 2 divided by L sine pi x divided by L V0 x divided by L into root 2 divided by L sine pi x divided by L into dx. So here 2 divided by L and V0 by L can be taken outside. 0 to L sine square pi x divided by L into x into dx. Right, now you can simply rearrange this as V0 divided by L into 2 divided by L integral 0 to L x into sine square pi x divided by L into dx. If you see this term, this is nothing but the expectation value of a one-dimensional infinite square well, which is nothing but L divided by 2. So we will be getting V0 divided by L into L by 2. That is equal to V0 divided by 2. Therefore, the first order correction in energy eigenvalue is V0 by 2. Option C. Three non-interacting bosonic particles of mass m each are in a one-dimensional infinite potential well of width a. The energy of the third excited state of the system is x into h cross square pi square divided by m into a square. the value of X in integer is. So in the question they have taken a 3 bosonic particles and it is inside a one-dimensional infinite potential well, and they have given the energy of a third excited state, and they have asked us to find what is the value of this X. So first we will write the energy of one-dimensional infinite potential well of with A. E of n is equal to n square pi square h cross square divided by 2 into m a square. Then we can write it as n square divided by 2 into k, where this k is equal to pi square h cross square divided by m into a square. Now we will find what is the possible way of arranging these three bosons in the energy levels. Now this is energy level 1 and this is 2 and this is the third level. Now all the three bosons lies in the ground n is equal to 1 state. So the energy in this condition is 3 bosons in the n is equal to 1 state into k. So that is going to be 3 divided by 2 into k. That is nothing but 1.5 k. 1.5. Now on the second possible arrangement is n is equal to 1, n is equal to 2 and this is n is equal to 3. 2 boson in n is equal to 1 state and 1 boson in n is equal to 2 state. So energy in this condition is going to be 2 bosons in n is equal to 1 state k plus 1 boson in 2 state into k. So by simplifying it we will be getting 3k. So the third possible arrangement is n is equal to 1, n is equal to 2 and n is equal to 3. 1 boson in n is equal to 1 and 2 boson in n is equal to 2 state. So here E is going to be 1 into 1 square divided by 2k plus 2 into 2 square divided by 2 into k. So by simplifying it we will be getting 4.5k. And the fourth possible arrangement is n is equal to 1, n is equal to 2, n is equal to 3. All the three boson in the n is equal to 2 state. So E is going to be 3 into 2 square divided by 2 into k. That is nothing but 6k. Now fifth possible arrangement is n is equal to 1, n is equal to 2 and n is equal to 3. So 2 bosons in n is equal to 1 state and 1 boson in n is equal to third state. So here E is going to be 2 into 1 square divided by 2 into k plus 1 into 3 square divided by 2 into k. So by simplifying it we will be getting 5.5k. Now we have obtained the energy levels for different possible arrangements of boson in different states. We will find which is the third excited state. This is going to be the ground state and this is the first excited state and this value is the second excited state and this is not the third excited state. This 5.5 is the third excited state. So in the question they have already given the energy of fourth excited state is x into pi square h cross square divided by m into a square. We have obtained E is equal to 5.5 into k is pi square h cross square divided by m into a square. So by comparing these two, we can write x is equal to 5.5. So in the question, they have asked us to write x in as an integer, that is 6. Consider the potential u of r defined as u of r is equal to minus u naught e power minus alpha r divided by r, where alpha and u naught are real constants of appropriate dimensions. According to the first born approximation, the elastic scattering amplitude calculated with u of r for a wave vector momentum transfer q and alpha goes to 0 is proportional to. So in the question, they have taken a potential u of r and they have asked us to calculate what is the elastic scattering amplitude, and when alpha goes to 0, the elastic scattering amplitude is proportional to what? So the scattering amplitude is given by f of theta is equal to minus 2 mu divided by q h cross square integral from 0 to infinity r u of r into sine qr into dr. Okay, in the question they have given the value of u of r. Now substitute it. F of theta is equal to minus 2 mu divided by q h cross square integral from 0 to infinity r into minus u naught e power minus alpha r divided by r into sine q r into dr. R and r will get cancels off, minus minus will become plus. So we will be getting 2 mu u naught divided by q h cross square integral from 0 to infinity e power minus alpha r into sine q r into dr. So from Laplace transformation, we get Laplace transformation of sine omega t is equal to integral from 0 to infinity sine omega t e power minus st into dt, that is equal to omega divided by s square plus omega square. So now by comparing these two, we can write q is equal to omega and alpha is equal to s. Therefore, we will be getting 2 mu u naught divided by q h cross square into q divided by alpha square plus q square. So q will get cancels off. We will be getting 2 mu u naught divided by h cross square into 1 by alpha square plus q square. So when alpha goes to 0, we can write f of theta is proportional to 1 by q square. A light source having its intensity peak at a wavelength to 89.8 nanometer is calibrated at 10,000 Kelvin, which is the temperature of its equivalent blackbody radiation. Considering the same calibration, temperature of light source having its intensity peak at wavelength 579.6 nanometer is dash. So in the question, they have given a wavelength and its corresponding temperature is calibrated as a 10,000 Kelvin. And also they have given another wavelength, and by using the same calibration, they asked us to find what is the temperature of the light source. This question can be solved by using Bain's law that relates the wavelength and temperature, that is lambda max into temperature is equal to B. B is a Bain's constant. So lambda max 1, we can take it as a first wavelength 289.8 nanometer and its corresponding temperature is 10,000 Kelvin. Okay, so lambda max 1 into T1, we take it as T1, that is equal to B. Let it be 1. Next wavelength is lambda M2 is equal to 579.6 nanometer. They have asked us to find the temperature, corresponding temperature. That will be lambda max 2 into T2 is equal to B. Dividing 1 divided by 2, you will be getting lambda M1 T1 divided by lambda M2 T2 is equal to 1. Therefore, by substituting all the values, we can have T2 is equal to 289.8 into 10,000 divided by 579.6. Here also 10 raised to minus 9, and here also 10 raised to minus 9. So by simplifying this, we will be getting T2 as 5000 Kelvin. For a two-nucleon system in spin singlet state, the spin is represented through the Pauli's matrix sigma 1, sigma 2 for particles 1 and 2 respectively. The value of sigma 1 dot sigma 2 is, in the question they have taken a two-nucleon system and they are present in the spin singlet state, and they have said sigma 1 and sigma 2 are corresponds to the Pauli's matrix of the particle 1 and 2. They have asked us to find what is the value of sigma 1 dot sigma 2. So for spin singlet state, the S value is equal to 0 and the corresponding S1 is half and S2 is equal to half. So we know S vector is equal to S1 vector plus S2 vector. Squaring both the sides, we get S square is equal to S1 square plus S2 square plus 2 times of S1 vector dot S2 vector. So now S1 vector dot S2 vector is equal to S square minus S1 square minus S2 square the whole divided by 2. In the question they have said it's a singlet state, so S value S square is 0 minus the eigenvalue corresponding to S1 square is 3 divided by 4 H cross, and for S2 square is 3 divided by 4 H cross square the whole divided by 2. By simplifying it, we will be getting minus 3 by 4 H cross square. So S1 vector dot S2 vector is minus 3 by 4 H cross square. We already know that S vector is equal to H cross divided by 2 into sigma. So S1 vector is equal to H cross divided by 2 into sigma 1, and S2 vector is equal to H cross divided by 2 into sigma 2. Now you substitute the value of S1 and S2 in this expression. So it will be H cross divided by 2 sigma 1 dot H cross divided by 2 sigma 2 is equal to minus 3 by H cross square. So sigma 1 dot sigma 2 is equal to minus 3. So answer is minus 3. The normalized radial wave function of the second excited state of hydrogen atom is R is equal to 1 divided by root of 24 a power minus 3 by 2 R divided by a e power minus R divided by 2a, where a is the Bohr radius and R is the distance from the center of the atom. The distance at which the electron is most likely to be found is y into a. The value of y in integer is dash. In this question, they have given the normalized wave function of second excited state of hydrogen atom. and they have given the electron is most likely to be found at a distance of y into a. They have asked us to find what is the value of y. So we know that for the most probable distance, the first derivative of probability function is equal to 0. P of r is r square into square of the radial function. So by substituting P of r here, we will be getting d by dr of r square radial function square, that is equal to 0. In the question, they have given the radial function. By substituting it, you will be getting d divided by dr r square into 1 divided by 24 a power minus 3 by 2 the whole square r square divided by a square e power minus 2r divided by 2a, that is equal to 0. So by taking the constant terms outside, 1 divided by 24 a power minus 3 by 2 the whole square divided by a square d divided by dr of r power 4 e power minus r divided by a equal to 0. Now we have to differentiate this term. So by differentiating it, we will be getting 1 by 24 a minus 3 divided by a square d by differentiating it. So we will be getting 4 r power 3 e power minus r divided by a minus r power 4 divided by a e power minus r divided by a, that is equal to 0. Now we will take the exponential term outside as a common factor. 1 divided by 24 a power minus 1, by simplifying these a power minus 3 and a power 2 into, we can take e power as a common factor. So we will be getting e power minus r divided by a into 4 r cube minus r power 4 divided by a. So we can write 4 r cube minus r power 4 divided by a is equal to 0. Then we will be getting 4 r cube a minus r power 4 is equal to 0. R cube we can take as a common factor. R cube into 4a minus r is equal to 0. So we can write it either r is equal to 0 or r is equal to 4a. Right? In the question already they have given r is equal to y into a. So by comparing with r is equal to 4a, we can write y is equal to 4. In the description box, you can find the solution for GATE 2018, 19 and 20 question paper. Please share and subscribe the channel.